So hello and welcome to MMA Design virtual discussion on CubeSat solar arrays. We are so fortunate to be able to have this opportunity to speak with you all today, and our goal is to inform you of what is actually needed to find the right solar array specific to your mission. My name is Leslie Steele, and I'm the Director of Teams here at MMA. And I'm joined today by Eric Gould, who is our Chief Technology Officer and resident solar array expert, and also Mark Bailey, who is our Director of Business Development. Eric and Mark work really closely with our customers what determine how our products can best be fit. And so today we thank you guys for participating, and we want to open this up eventually to discussions that you guys may have questions you want to answer. But before we open it up to you, Eric, can you tell us about MMA solar array offerings and what makes it different from other solar arrays?
I will. I noticed there's someone waiting in the lobby. Are you able to admit them in? Hello, thanks for joining. I'm Eric Rule, I'm the CTO of MMA. I was just posed a question to describe what MMA offers in the world of solar arrays and what makes us unique among the industry. So MMA has been providing solar arrays for space missions for more than a decade. Primarily for CubeSat missions, we've delivered and launched 7 missions so far, and we have almost a dozen more that have been delivered awaiting launch. And our specialty has been in high performance arrays. And there's some key metrics that are used to determine what is a high performance array. The 2 most popular are watts per kilogram. How efficient is your mass of the array? So that ideally you would have just solar cells, but the solar cells still require some structure to support them in the stowed and condition, and then when you deploy them and provide that structural support behind them. So how efficient is the mass in your design? Watts per kilogram. And the second metric is kilowatts per cubic meter, which conveys how efficiently you package all of that power into a very small stowed envelope. And those are the 2 areas where MMA really excels with our custom designs, our architecture. We have a unique launch restraint system that has a very, very low profile to it, not much thicker than the stack of the panels itself. So in all of our CubeSat arrays, we're able to provide a solution that doesn't penetrate the bus surface at all. And we're able to really optimize our packaging on the surface. There's a third key metric in the industry, which is, of course, is dollars per watt. And we're always trying to work to be more efficient at that as well. Our solar arrays, we cover solar array opportunities for anything from 3U solar CubeSat up through 16U. There's someone else waiting in the lobby. And so we have a variety of design configurations that we've already come up with and likely have delivered. And we have a SATA design that is also an option for CubeSats that fits across the width of a 1U thickness spacecraft, such as a 3U or a 6U, or it can be oriented the other direction. We have a 2U depth solar array. It's a pancake design, SATA, so that it has a very shallow height to it to minimize our envelope on the spacecraft. And that SATA design is convenient in that it incorporates the control electronics into the SATA itself. So you need only provide power and then a RS-422 connection to supply the commands to it. There's no separate motor driver needed for it. It's all built into one convenient assembly. And then as we look towards small sat systems, we have delivered a solar array for a small sat recently, where you could call a very large CubeSat, didn't fit into a canister, plastic canister. And we also have designs naturally for larger rigid panel arrays or even boom deployed arrays, often considered as blankets, where we can leverage all of these technologies that we've developed in the CubeSat world we can leverage all of that technology, our very thin film, our very thin substrate solar arrays that provide radiation shielding to the backside of the cell. And we can populate a deployed boom with many of these thin panels to produce kilowatts of power in a small sat class or ESPA class spacecraft. Anything like to add to that?
No. Let's talk about how we go about helping people with figuring out what they need.
Sure.
Yeah, so what are some of the things here at MMA that we need to know in order to provide customers with cost estimates and timeline?
Well, let's start at the beginning. Actually, let's start at the end, because typically mission is driven by the end-of-life power. So that as a satellite lives its life in space, it degrades, the solar array degrades because of radiation, because of the environment it's in. And so what we need to actually size the array for is the amount of power you need at the end of your life. Or if you're particularly electric propulsion driven, maybe at the end of your mission to get to the station keeping that you need to hold. But in any case, we need to know what that power is that you need at the end of all that degradation so that we can size your arrays appropriately to get you what you need up front. So some of the things that we will typically ask for are, well, first of all, what is that end-of-life power requirement? What are the temperatures that you're going to see? If you don't know, we can kind of put in some generalized numbers to start with, but eventually we'll need to know that maximum temperature at hot and the maximum temperature, the minimum temperature at cold, because that definitely has an impact on how the array performs. We'll also need to know what orbit you're going to be in, or if you're not going into an orbit, you know, what environment you're going to see in deep space. We'll need to know that lifetime. Is it a 1-year mission, a 3-year mission, a 5-year mission, a 10-year mission? All of that is important to know. I think those are the main questions that we typically start out with. And then it also really is important to know what your power control electronics look like, because it definitely makes a difference if you are a direct energy transfer system or if you are a peak power tracking system. So all of that are kind of the first fundamental building blocks that we have to know.
So let's pretend I have a new CubeSat mission. It sounds like a lot of these questions are something that I would have to know to find a solar array that fits my needs, right?
Absolutely.
So you mentioned the SATA. Can you tell me more about that?
Yeah, as I mentioned in the introduction, we have a SATA design that fits on multiple CubeSat configurations. And we have a few of those opportunities coming up for launch. 2 of those are going to the moon, and one's going to a deep space opportunity on the upcoming SLS missions. And the nice thing about the SATA solar array drive assembly is that it allows you to point the solar array to some orientation other than what the spacecraft is looking at, so that you can optimize the sunlight that you're capturing on the solar array. And we'll need to know if you need that SATA in order to really optimize your power output per orbit or during your mission life, so that you can really maximize that, capturing that sunlight over the mission. If there's most of our specifications that we receive are specified in terms of peak power requirements, whether that's again, using a peak power tracker control system or it's a direct energy transfer control system. But sometimes we'll encounter one that has an orbital average power, and we'll need to calculate what power is necessary and if there is a SATA or not, and what those off-pointing angles might be to account for that loss of sunlight. So the SATA really allows you to optimize your power for a given footprint by ensuring that it's always pointed optimally at the sun, so, regardless of where the spacecraft is pointing.
A couple more questions regarding the SATA. Do they work interplanetary? And also, is there single and dual access? Sorry.
Yeah, you want to do that one or me?
Yeah, I'll do. So yeah, typically our baseline design is a single axis design. So it will just track the arrays in the alpha axis. The beta axis can be done by just putting the motorized hinges on the ends of that SATA so that we can get dual axis control of the panels if necessary. It would require additional motors and additional controllers for that to happen. You asked if they could work interplanetary. Of course they can. Of course they can. And in fact, sometimes it's critical for interplanetary missions to do that. Although our first interplanetary mission, Marco, did not have a SATA on it, so it's not critical. It depends on what your power requirements look like. One thing that Eric didn't mention is we actually did already fly one of these SATAs. It was on a commercial mission that we've not been given permission to share information on, but the SATA does have flight heritage already.
And are there minimums or maximums the SATA can handle?
Yes, so we actually have different designs for handling different power levels. For example, our original one was designed for our standard Hawks, which is about 42 to potentially 84 watts. But the LunaMap mission that's going to be going on SLS was 112 watts of power. So we actually had to size that SATA up a little bit more. So instead of the standard SATA, which is about 8 millimeters thick, the SATA grew to about 10.5 millimeters thick, something like that, in terms of its stowed height, how it sits on top of the bus. So the SATA does have to grow slightly to handle more power, but we can size it for the power.
So let's say that I need 100 watts BOL to be sure I have 90 watts at the end of life. Is that enough to determine the array for my mission?
No. We'll also need to know a little bit more about your power control system. We hinted a little bit about if it's a direct energy transfer system versus a peak power tracker system. So we'll need to know that, as well as how many channels you have available on the power control system, and if they're what the current limits and voltage range limits are of that. Back on the SATA, I also wanted to mention really quick, in addition to sizing the SATA to be able to accommodate the required amount of power in the harness coming across that hinge line, we also can size that SATA according to any deployed first mode frequency requirements, because that SATA connection really is the root connection for the wing to the spacecraft, and that's what dominates usually your first mode of the deployed wing.
What is the current limit per circuit?
Typically, we're sizing for less than 2 amps per circuit, but that can be mission specific.
So great.
Each string of cells typically in these CubeSat arrays are putting out about a half amp. So that allows us to place several strings in parallel while staying below that 2 amp limit. And that can minimize the number of harness wiring that comes across that joint.
Wonderful. So now are we ready to get our array? I mean, do we have everything that we need to give you?
No.
So yeah, we actually need to know things like, well, one of the things important to know is, are you in a canister or not? One of the things that you can see here, so this is a standard Hawk design, and this is what Eric was talking about our low profile restraint system that goes around it, and this is designed to fit into a typical CubeSat canister deployer. When the release device is triggered, then the panel is freed up to do its deployment. We won't do the deployment. But some missions don't sit in a canister, so that certainly gives us some other degrees of flexibility. There are some interesting things about fitting cells into canister. On our very first launch for the JPL Asteria mission, we were able to launch with 3 rows of standard cells on the panel. You can see it had it on both sides, and there were actually some body-mounted cells on the satellite as well. Those 3 rows of standard cells don't typically fit. Let's see better now. Those 3 rows of standard cells don't typically fit on either side of the bus, because on the other side, there's often rails in the canister deployer that restrict the volume. So putting 3 rows per cell is possible, but not always easy. We did do one other mission where we put on 3 rows of cells. On the BioSentinel mission that's going to launch on SLS. And you can see the 2 sides, so it does fit on both sides, but we had to forego the restraint system. So this one actually uses these little rollers here to actually keep the array constrained by the canister itself, which is really clever, but it also, as you can see, creates a handling issue, because now this is sitting on your bus unrestrained, and the panels are definitely at risk and need to be handled with an extreme level of care when you're handling the arrays. So some of the things that will help us to know that if you do need more power and you need to fit in a canister, we've actually designed a custom cell that still fits 3 cells in, and actually 8 cells per string rather than the typical 7 that would fit from the standard cell. And so this lets us put in 50% more power into a given CubeSat array.
These would install on the same face of a CubeSat. So it's a 6U or a 12U. On a 12U, that can fit on any sides of the 12U bus. So with the custom cell size, we're able to optimize our footprint. If you look at this wing installed on that face of the CubeSat bus, there's an unused area around the array because we couldn't guarantee that this could go on any face if we had 3 strings wide. It would only fit on the top surface of the 12U bus because we still need some room for a launch restraint. That's still our preferred method. We really don't prefer using the canister as the launch restraint. There's so much unknowns. There's so many interfaces there that are beyond our control when we're designing, and it can be very challenging. We've done it successfully. Whenever there's an opportunity to decouple the launch restraint from the canister itself, that's always of value. We prefer that. So.
Wow, that looks like a lot more power. So what else do I need to know?
A little bit about the mission. I mentioned earlier about first mode frequency. That comes into play on some missions where there is a precise pointing requirement of some other instrument that's on the spacecraft, or the spacecraft needs to have a high level of agility so it can rapidly point to other locations. And the last thing that they want to have is a floppy solar array that's causing a lot of jitter and shaking, and they have to wait for that to settle out. So that can drive the deadband requirement in the array so that when they move, there isn't any kind of low frequency oscillations that occur across the deadband in any of the joints, as well as having that frequency of the rigid array. So we need to know a little bit about the mission and the footprints and envelopes, obviously, any kind of stay out zones that are on the bus surface, because we're mounting and covering up potentially instruments that would be on that surface that may be revealed upon release and deployment of the wing. We need to know where those are so that we don't contact them when we're stowed up.
Or obstruct their field of view
When we're deployed. Yeah.
Okay, awesome. So that's a little more complicated than I'm sure a lot of people imagine. So I think at this point we can open it up to questions to everybody in our audience.
There are actually, we've had a few missions that have very tight magnetic dipole requirements.
Yes.
So those need to be factored in if we need to design the layout of the panels in order to cancel those dipoles. There are all kinds of interesting things that we can do and have been asked to do, like including temperature sensors or release indicator feedback, telemetry. So there's lots of things that are possible and things that would be helpful to make sure we actually truly specify that down to what you really need, because you certainly don't want to get those as a surprise later when you say, oh yeah, by the way, I actually also wanted to have this piece of information or that device. So all of that's important to know.
Yeah. Speaking again with a little bit more about magnetic moment, that's dominated by the layout of the wiring on the backside of the panel and how closely that follows the layout of the strings on the front side of the panel, minimize those current loops that occur due to that offset. And another mission requirement might be if there is a requirement for redundant wiring. A lot of these CubeSat designs don't have redundant wiring. Now, the wire itself is inherently redundant because it has multi-strand in it. It's not solid core wire. But some missions require very high reliability, and there are requirements for redundant wiring. We need to know that because that can affect directly the parasitic torque across these hinge lines so that we can properly size the springs in the hinge lines to overcome that torque requirement.
You can see there's a lot that goes into this.
Hey, Leslie, there's a question from Jonathan. Is there a common ratio to target for peak power to average power consumption, or is that more of an orbital ConOps issue?
That's specifically an orbital ConOps issue. And typically the customer does that because they have all the insights into their pointing angles and throughout their mission, and they can identify that worst case orbit over the mission life for the solar season and Earth season around the sun, and they can account for that. Now, if needed, we can help with that. We know how to perform all that analysis, and that might be dynamic throughout the mission, initial development of the mission requirements. So typically, it's more efficient for the customer to manage that and then convey to us what the resultant peak power required is necessary in order to meet that orbital average power requirement. So we can assist you with that, but typically it's better if you manage that side of the mission ConOps and just tell us how much peak power you need at the end.
Okay. There's another question from Mike. I've read all the SMAD panel sizing exercises, etc., but what I've never understood, if you oversize your panels and your battery recharges too quickly, do you have to radiate the extra collected power to avoid overheating the CubeSat, or is this somehow a self-correcting problem?
There's several different ways that you can limit the amount of power that's going into the battery, and a lot of that depends on the power control system that you're using. If it's a peak power tracker system or if it's a direct energy transfer system, you may have some connections in there that you could open up a relay and basically disconnect some number of strings so that those strings are still generating power, but that power is staying on the wing and it's electrically disconnected from the battery, and you're running on a fewer number of strings in your system. Now, if there are strings wired in parallel, you might end up, depending how it's wired together, if both the positive side and the negative side are connected in parallel, then you can't differentiate between those two. So you would be turning off both of those together. But even if they share a common ground, as long as there's a unique power that's coming off, you could disconnect one string from the other and then just run on that one power. Another option is to point the solar array away from the sun. Just change your angle of incidence, and that will reduce the current. It won't change the voltage. The voltage is not really incident or intensity sensitive. If there's any light there, you'll get almost all of the voltage, but the current will be very low unless you have optimal illumination. So you can modify the current just by tilting the array a little bit away from the sun.
But if I look at an IV curve,
And then if you're body mounted or body fixed, so
yeah,
because that obviously might interfere with your ConOps if you have while you're trying to perform your mission.
Yeah, I know there's another question coming up here, but again, back to that heat problem. As MMA has continued to evolve and optimize these arrays, we're now getting several hundred watts of power available into a very small CubeSat bus. And that power management, that thermal management problem, is a real issue, and not just for the battery, but for all the other instruments that are in the bus. You have an awful lot of power coming in, and things don't operate at 100% efficiency, so you're generating a lot of heat. And that absolutely needs to be considered on the mission side in the bus architecture.
Can you guys hear me okay?
Yes, I
Yes.
can. Go ahead.
Oh, okay. Yeah, so I was just trying to ask, if I look at an IV curve, I see the current basically goes to 0 as you reach the open circuit voltage.
Yeah.
So I'm trying to figure out, does your panel treat a charged battery as an open circuit?
No. I'm going to assume you're working here with transfer. So the solar array is clamped directly to the battery.
Let's assume that for simplicity.
Okay. So in our design, what we'll ask you is, what is the operating range of the battery in terms of voltage? What's the lowest voltage and your nominal voltage? And we will design the array also looking at that same current versus voltage curve, the array, so that you have that knee in the curve where it starts dropping down towards the VOC. We'll design the array so that that knee is outboard of your operating range, so that effectively the array is operating as a constant current device.
Yeah.
Tends to make the power design a lot simpler.
But so it still does have to drive current, even if you're fully charged. The panels necessarily have to drive current somewhere, even if this directly charged battery is fully charged. Is that right?
It's clamped to the battery voltage, so what you'll find is the power coming out of the array is limited by the current battery. And the array is being forced due to that constraint that you're forced to operate at that voltage. So if you alternatively at the power versus voltage curve, which naturally both of these curves change with temperature. When you're looking at that power versus voltage, you'll notice that in a direct energy transfer system, a lot of power off to the right that is just not being used.
Yeah.
All that power because you were forcing the array to operate at that lower voltage.
Okay. I still don't get it. I've been to 10 of these seminars and I still don't get it. All right.
Do we have any other questions?
It's the values of a peak power tracker system. When you're looking at that power versus, and you see that you're clamping the array to a lower, you're losing all that power. It's not available to you. That's the real benefit of a peak power tracker, is it's changing the resistance in the system to allow the array to operate at its maximum power point.
Yeah, I have a peak power
efficiency.
Actually. I have a peak power tracking system. I still just don't understand what happens to the panels, whether electrons are still flowing through the panels when the battery is fully charged.
Power is being left on the array, so the array will be hotter.
Okay.
Not pulling the power off of the array. So
Great.
in case your survival temperature, you'll need to take that into account, assuming you're not drawing any power from the array.
Yep.
Trying to generate power, so all that heat is staying on the array.
So that's
pulling power off, that the wing will run a little bit cooler.
So if my conversion efficiency is like 30%, I basically have to assume when the battery's charged, I'm getting that extra 30% as purely thermal flux on the panel. If I'm usually converting, so let's say we have 1,300 watts from the sun. If I'm 1,300 watts per meter squared, if I'm usually converting 30% of that to electricity, if I'm not using that, if I'm leaving that power on the panel, that just means I have an extra 30% of solar flux to deal with. Is that right?
I think I may have conveyed it to you back in the when the battery is fully charged and the power is effectively staying on the panel, it doesn't mean the power is heating up the panel. What I'm saying is the cells are sitting there as if there's no current. So you can just treat that as a thermal mass, and you just activity and emissivity and the specific heat of those components, and you can determine what your temperature is. If you are pulling power off, it will.
I missed the last thing you said, but I think I get it now. Thanks very much.
Okay.
Do we have any other questions? Well, we really appreciate you joining us today, and if you do have questions that arise, please feel free to reach out to us via email at mmadesign.llc.com. And yeah, thank you guys so much for joining us, and have an awesome day.
I'll add a couple more party comments in here. So we discussed all of these pretty in-depth level of requirements that we look for, right? What's the mission? How much power do you want? Is that the beginning or the end? What are the temperatures that you're going to see, et cetera? How much envelope does it have? What's the first frequency? It's a lot of information. And then we take all that information and we try to optimize the wing for your specific mission. And what we do is we'll look at all of the major suppliers of the solar cells, the performance of their individual cells that they offer, the different sizes of cells that they offer, and then we will tailor from what's available, we'll tailor that to give you the optimized solution. Now, we have several designs for the CubeSats, canisterized CubeSats, so there isn't a lot of work that goes in there. It's usually down to the cell selection. What cell do we want to use on this mission? Are we going to do a 7-cell string or a 14-cell string? How we're going to wire up the wing? But as you get into the small sats and larger, the envelopes of the panels are not as standardized as effectively in a CubeSat. So there can be a lot more variety in the small sat and larger stuff. But we take all of that information that is provided to us, and we have some proprietary design tools that we can rapidly do some trade studies on different cell types and different cell sizes, all for your given mission envelope, and come back with these optimized solutions and tell you how much power we can fit. Because ultimately, in those custom arrays, it becomes like a Tetris puzzle trying to solve not just the cell size, but the string size, the string footprint, and seeing if we can get the optimum cell size and string length so that we can maximize that fill factor on the panel while respecting any stay-out zones that are necessary for launch restraints, other instruments, coarse sun sensors, et cetera, that might be on the surface. So that's why it really helps us to understand all that, not just the power, but what's the voltage and the temperature and the radiation environment, and you need that power at the end, beginning, et cetera. So it's really a lot more than just how much power do you need.
Right, because if you buy a lot of power, you may not have it at the right voltage, you may not have it at the right current, and so you may end up buying a solar array that doesn't really fit your power control electronics or your mission profile.
Yeah, and then here at MMA, we deliver systems. We don't just deliver panels with cells on them or strings of cells. We deliver a deployable system that you can take and bolt it onto your spacecraft. It comes integrated with all the launch restraints. It's been tested as a system with the launch restraint. You can install it onto your bus, connect it to your power control system, and you're good to go. There's no additional assembly or testing that you have to do at the subsystem level. It's built, tested, and delivered as a system, complete system.
Even with the SATA has its own built-in control electronics. So everything is designed to be modular and bolted on.
Awesome.
Thanks.
Thanks, everybody.
Thank you, everyone, for stopping by.
Yeah, thank you.
Appreciate it.